This video is over logistic growth by Alyssa Garza. Logistic growth is typically used when describing population. There often exists some upper limit, L, for which growth cannot occur past. L is called the carrying capacity, or the maximum population YT can sustain as time T increases. P is going to equal the population, L is going to equal the carrying capacity, K is going to equal the growth rate, and T equals time. The logistic growth equation is dP over dt equals Kp times L minus P. The general solution is P equals L over B times E to the negative Lk T plus 1. And in order to get B equals L minus P0, the initial population, over P0, the initial population. The logistic growth graph on the left shows that when T equals L2, P is growing its fastest. And the general solution graph on the right shows that L over 2 equals an inflection point. And the limit as T approaches infinity of P equals L, the carrying capacity. Now with those, we're going to do a skill question. This skill question reads, biologists stocked a lake with 400 fish and estimated the carrying capacity to be 10,000. The number of fish tripled in the first year. So with that, I wrote down what we know. And L, the carrying capacity, is 10,000, and P0, the initial population, is 400. Then it said after the first year, the fish tripled. So my point is 1/1200. Back to the question, A says, assuming that the size of the fish population satisfies the logistic equation, find an expression for the size of the population after T years. This means we're going to use the general equation. So P equals L over BE to the negative L KT plus 1. First, I found B equals L minus P0 over P0. So B equals 10,000 minus 400 over 400, which equals 24. Next, I plugged in my B as 24 and my K's as 10,000. Then I plugged in my point 1, which is time, and 1200, which is population. So my new equation reads, the population of 1200 equals 10,000 over 24 times E to the negative 10,000 times 1 times K plus 1. Then I started to solve for K, so I cross-multiplied and got 10,000 over 1200 equals 24 times E to the negative 10,000 times 1 times K plus 1. Then I minused 1 from both sides, then divided by 24. And then to cancel out the E, I took the ln. So the new equation reads ln of 10,000 over 1200 minus 1 over 24 equals negative 10,000 K. And from here, I continued to solve for K. So then I divided by negative 10,000, and K equals negative 0.000118562. I rewrote my general solution as P equals 10,000 over 24E. And then I combined my K and my negative L to make one number as negative 1.18562T plus 1. Back to our skill question. B reads, how long will it take for the population to increase to 5,000? So in the next part, P is going to equal 5,000, which equals our general equation. So then I solve for T, the time it will take for the population to increase to 5,000. I cross-multiplied. I minused 1 from each side. I divided by 24, then took the ln, and my T ended up being 2.68 years. The last question of our skill question reads, what is significant about the population size of 5,000? When the population is 5,000, P will be increasing the fastest, and this is because L over 2 is when P is growing the fastest at this time. And since our L is 10,000, and 10,000 divided by 2 is 500, this makes this true. The next question we're going to do is our AP question, and this question is from 2004. The problem reads, a population is modeled by a function P that satisfies the logistic differential equation. dP over dt equals P over 5 times 1 minus P over 12. Question A says, if P of 0 equals 3, what is the limit as T approaches infinity of PT? Now, from earlier we know that the limit as T approaches infinity of PT equals L, which is the carrying capacity. And in this equation, the carrying capacity is 12. So the limit of PT as T approaches infinity is 12. The next part of the question read, if P0 equals 20, what is the limit of PT as T approaches infinity? And the answer is also 12. No matter what it is in the equation, the carrying capacity will always be 12. B reads, if P0 equals 3, for what value of P is the population growing the fastest? From our graph, we saw that the population grows the fastest at L over 2. And we said earlier that our limit was 12. So 12 over 2 equals 6. So that is when P is growing the fastest. C of the AP question asks, a different population is modeled by y that satisfies the separable differential equation dy over dt equals y over 5 times 1 minus t over 12. The equation is just like the first one, but it is y variable instead. So this one says, find yt if y0 equals 3. So in order to do that, I rewrote the equation. Then I separated my variables, so my y was on one side with my dy, and my t's were on one side with my dt. Then I took the antiderivative of each side in order to get the ln of y equals t over 5 minus t squared over 120 plus c. Then I raised them all to e to get rid of the ln. So now the equation reads y of t equals, I brought down my c variable to the front, c times e to the t divided by 5 minus t squared over 120. My c is my initial population, and since P0 equals 3, my c equals 3. So y of t equals 3e to the t over 5 minus t squared over 120. The last question of the AP question asked, for the function y found in part C, what is the limit as t approaches infinity of y over t? The limit as t approaches infinity over y over t, and y over t is 3 times e to the t over 5 minus t squared over 120. The limit is 0 because y over t is exponential, and it is logistic growth equations that have carrying capacities. And that's it.